The workshop is Professor Vassiliev from University College London, and he will speak on spectral theory of first-order systems, interface between analysis and geometry. Thanks.
Thank you. As this is the last talk, I feel it would be appropriate to thank the organizers on behalf of all the participants. So thank you, organizers, for bringing us all together at this wonderful workshop. Okay, so I will be studying initially an abstract problem. I will be working on a compact and dimensional manifold. It will not have a boundary. I want to make my life easier. And I'll be studying a system of equations, a first-order system. So M by M matrix operator A. So it's a system of first-order pseudo-differential operators for generality, and I'm studying the spectral problem. I'm interested in the eigenvalues and eigenfunctions of this problem. Now, I assume this problem to be elliptic. My definition of ellipticity is that the determinant of the principal symbol is non-zero for non-zero momenta. I do not require it to be positive. It's not necessary. So principal symbol is denoted like this. It's a matrix-valued function on the cotangent bundle. And the eigenvalues, I denote them by Hj. So they're exactly M eigenvalues. I assume them to be simple. For my analysis, it's important they are all simple. So I'm studying the simplest possible situation. I do not assume that they have a particular sign. Some of them are positive, some are negative. The notation H is chosen because eventually they take on the role of Hamiltonians, these eigenvalues of the principal. Okay, I'll be studying three objects. The first object is called a propagator. So here is its definition. If you look carefully, it's the operator that solves the dynamic problem. If you add time, as you do say in the Dirac equation, you want to solve the Cauchy problem for the dynamic equation. This operator gives you the solution. It's an expansion in terms of eigenvalues and eigenfunctions of the operator, which unfortunately we don't know. But if we knew them, this is the definition of the propagator. And I denote it by capital U because, of course, it's a unitary operator. Now, the second object that I'm studying is called the spectral function. So at every point x of the manifold, I take the squares of the eigenfunctions at this point. These are columns, of M elements, so Euclidean norms, square, and sum over all eigenvalues between 0 and some positive lambda. People who work, in spectral theory are familiar with this object. It's called the spectral function. And finally, a much easier object, the counting function. It's simply the number of eigenvalues between 0 and a positive lambda. I do not count negative lambdas in this talk. If you want to count negative lambdas, just replace the operator A by minus A. But this is important because there is a spectral asymmetry in this problem. When you have spectrum going to plus infinity, minus infinity, there is no reason for the spectrum to be symmetric. So counting function actually is expressed nicely through the spectral function. It's just the integral of the spectral function. So these are the three standard objects that people study in spectral analysis. Now, what are my objectives? First of all, I want to construct the propagator explicitly. Now, it's a tall order. You have to know all the eigenvalues and eigenfunctions. But I do not want to construct it absolutely precisely. I want to construct it modulo an integral operator with smooth kernel. I am prepared to lose all smooth contributions, which is sensible when you're studying propagation of waves. Normally, you're interested only in propagation of singularity. If you lose smooth bits, it's not that important. And the objectives 2 and 3, are traditional objectives for people working in spectral theory. Derive two-term asymptotic formulae for the spectral function and the counting function. So this sort of problem is standard and classical. Now, how does one do it? There is a technique for constructing the propagator explicitly. It's called microlocal analysis. You write the propagator as an oscillatory integral. So enormous oscillatory integral, you spend months, years differentiating, you can write it down explicitly. The idea is you start with Hamiltonian trajectories. They sort of like classical particles. They determine the skeleton on which you later add waves. There is a procedure for doing it explicitly. This procedure resembles, I'm just giving explanation for those who are unfamiliar with microlocal analysis. This procedure is somewhat similar to writing Feynman diagrams, but the small parameter in microlocal analysis is the variability of coefficients. You are working on a manifold, so the coefficients are bound to be non-constant. And the way microlocal analysis works is, you see, okay, let the coefficients be constant. I know how to do the Fourier transform, I can write the propagator and everything. And then I remember, oh, the coefficients are not constant, so I better make a correction. And this gives you an iterative procedure for writing these oscillatory integrals. Okay, an important key word in this subject is Fourier integral operator. A Fourier integral operator is a way sort of writing all waves simultaneously, all the waves, but in one big pack. Like this gives you the propagator. The nice thing about this whole construction is that it gives a meaning sort of to physical terms. A physicist would say, I'm constructing a wave packet. But a pure mathematician would say, I'm constructing a Fourier integral operator, and it's all kosher, it's all proper pure math. Where can one read this stuff? And once you've constructed the propagator, the other bits, objectives 2 and 3, are straightforward. It's known how to do it using Fourier-Tauberian theorems. The main thing is constructing the propagator. Propagator has its own, interest anyway, irrespective of whether you are doing spectral theory or not. But okay, sources. Hermander. 4 volumes. Unreadable. I don't know a person who's read it. I've read one chapter. And there is here book. Safarov and Vassiliev. Only 1 volume. Now, I've been reading my own book lately, and it's still not easy enough. So somebody should write a really popular, good introduction to microlocal analysis. We never managed to sell it to the wider community. We never managed to sell it to the applied maths community. But it's a perfectly applied technique. Now, why am I giving this talk today? All this was done 32 years ago. Okay. So in 1980, Victor Ivry published a formula for the second asymptotic coefficient. And it was wrong. Now, what happened, I think I understand what happened. It was the year when he proved the Weil conjecture for the Laplacian in a domain with a boundary. It was a great result. There was great excitement. There were rumors that he was considered for the Fields Medal. I don't know whether it's true or not, but he was twice invited to give talks at the International Congress of Mathematicians, and twice the Soviet authorities didn't allow him to travel. So great excitement, he tried probably to announce as many results as he could. The result for the Laplacian was definitely correct, and he thought that for systems it will be the same. He thought that the second asymptotic coefficient would be proportional to the subprincipal symbol. Okay, those who know, I don't know this terminology, subprincipal symbol is the lower coefficient written in invariant form. So he thought for a system, the second asymptotic coefficient will be proportional to the subprincipal symbol, as it is for a scalar operator. And it's not. Even if your subprincipal symbol is 0, you still get a non-trivial second term, because a system is fundamentally different from a scalar equation. Anyway, in 82, he published another paper where he stated that the previous formula was wrong, gave another formula. Roughly the same time as in blue. But it was also wrong. It was still linear in the subprinciple symbol. Rosenblum at roughly the same time published a similar result, also incorrect, also linear, proportional to the subprinciple symbol. I have to be careful here because I submitted a paper to Journal of Spectral Theory. You have to submit to the editor who is closest to the subject, and obviously I submitted to Rosenblum. Okay, but by 84, Ivry realized that things are not so simple. He published a book in Springer Lecture Notes where he stated that all his previous formulae for systems were incorrect, and he couldn't give a formula. He gave an algorithm. If you succeed in decoding this algorithm, which involves integration over contours in the complex plane, going to limits, you end up with a sum of 3 times m to the 5 terms. M is the number of equations. So if m is 2, you have 96 terms to add up, and these are pretty complicated expressions. Okay, so this same algorithm appears in the 98 book of Ivry, and I think there is a new book due this year, which will be 3,000 pages long, also in Springer. But in 1989, Safarov published a formula. Okay, it didn't publish in a journal, but in his Doctor of Sciences thesis. And this formula was perfectly sensible and took account of effects coming from the principal symbol. So here he realized that things are not as simple for systems. I wrote a positive report for this Doctor of Sciences thesis, and I thought the formula was correct until recently I realized it's also wrong. It doesn't invalidate the thesis. That was a sort of not the main result of the thesis. Now, in 98, I asked a PhD student of mine to rederive Safarov's formula using a slightly different technique. He couldn't do this in full. The calculations are massive. But he checked that Safarov's formula for the principal symbol of the propagator was correct. So we knew at least up to a certain point where we stood. In 2007, Kamotsky and Rozhansky published a long paper where they developed Rosenblum's technique. The paper ends up with a theorem. There is a two-term asymptotic expansion for the counting function, but we will not give you the second asymptotic coefficient, which was a wise move. Now I think we know, after 32 years, we have a formula for the second asymptotic coefficient, and I'll give it to you now.
Is it correct?
I think it is, and I'll give you reasons why it's correct. It's unitarily invariant. That's a good reason. I'll give the reasons in a couple of minutes. So, Safarov's formula, some sort of integral. This is the term everybody saw, and this is the term which he added. The term, okay, the non-trivial term coming from the principal symbol, from the sort of non-commutativity of matrices. And he used the concept Poisson bracket on matrix function. You see, you can write Poisson brackets not only on scalar functions, but on matrix functions. It gives you an invariant object. You just have to be careful not to change the order of matrices. So he wrote a formula which was perfectly sensible. What made me worried eventually was when we started testing unitary invariance. So if you multiply your operator by a unitary smooth, matrix function on the left and the right, you don't expect the spectrum to change. You don't expect the spectral function to change. But when we tested Safarov's formula, it was not unitarily invariant. By the way, it's not easy to see whether something is unitarily invariant or not because there's some integration by parts involved and so on. So we eventually established something was missing. And now I'll give you the missing bit, and it's beautiful. Okay, it's a beautiful mistake to miss such a bit. So what's happening? When you are working with a system, you have to work with the eigenvectors of the principal symbol. These are not the eigenvectors of the operator, no, eigenvectors of the principal symbol. Much simpler object, you would think, just linear algebra. But you have a problem. They are defined only up to a gauge transformation. You can multiply them by e to the I phi, and it's still an eigenvector of the principal symbol, linear algebra. And this thing is this gauge transformation. It's bound to show up somewhere. Gauge transformations are not as harmless as you may think. And it shows up as a U1 connection. You can start thinking, if I don't know how to uniquely define an eigenvector of a matrix, maybe I can at least have a connection. If I have 2 points, in the cotangent bundle, maybe I can parallel transport an eigenvector of the principal symbol in such a way that it remains orthogonal to itself along the curve. So there is a natural parallel transport in this problem. And it gives you essentially a covector potential. Those who work with electromagnetism know what a covector potential is. And here it's just written explicitly in terms of the eigenvectors of the principal symbol. The only difference with your usual covector potential, everything happens on the cotangent bundle, not on the original manifold, but on the cotangent bundle. So it's slightly more general situation, but it gives you a curvature tensor, which you can calculate explicitly. It's an analog of the Maxwell tensor, but living in higher dimensional situation on the cotangent bundle, 2n by 2n object. And then, because you have a special structure, you have position variables and momenta, you can take a trace with a normal Maxwell tensor, electromagnetic tensor. You cannot take its trace. Okay, you can take it, but you get 0. But here you can take a trace of this block, and it gives you an invariantly defined scalar object, which I call the scalar curvature of the U1 connection. And this is the term that Safarov and everybody else missed. It's bound to appear in microlocal analysis, but okay, how does it appear? When you do all this microlocal analysis stuff, you write your propagator as a sum of m oscillatory integrals. M is the number of equations. You have m Hamiltonians, m different waves, so you have to write m oscillatory integrals. And this curvature of the U1 connection has to show up in lower order terms of the propagator. Problem is, nobody knows how to define the subprincipal symbol of a Fourier integral operator. For a pseudo-differential operator without time, the concept of a subprincipal symbol is well defined, but not for a Fourier integral operator when you have time. But you can look at what happens at 0. At time 0, each of these is a pseudo-differential operator. And you can define the subprincipal symbol, take the trace, and magically you get the curvature of the U1 connection. Of course, if you add them all up, you get 0, because they add up to the identity operator at time 0. The propagator at time 0 is the identity operator, because you are solving the Cauchy problem. But everybody thought that if they add up to 0, they have to be 0 separately. They are not 0 separately. Okay, so here is the correct formula. Here is the missing curvature term. We tested it for unitary invariance. It's all fine. But there will be another test in 5 minutes. But the bottom line here is that whenever you are studying a system of equations with variable coefficients, there is an internal electromagnetic field sitting inside it. It's written down explicitly, and if you want to write correct formula, you have to take account of it. It's just an abstract fact. It has nothing to do, with spectral theory or anything. For some bizarre reason, people who did analysis of systems never noticed that this internal electromagnetic field, the corresponding curvature. Okay, now I'll analyze a special case. I want to make my problem simpler, so I'll look at the case when the dimension is 3, number of equations is 2, the operator is differential as opposed to pseudo-differential. I don't want, absolute generality. And trace of the principal symbol is 0. It's the simplest possible type of system. Okay, I'm lying a little bit. Simpler would be dimension equal to 2. But I cannot handle dimension equal to 2. There are some geometric issues which I cannot deal with at the moment. So almost the most simple case. And it's also important for obvious physical reasons. The massless Dirac operator in dimension 3 will fit into this scheme. So there are simplifications in this case. The main simplification is that the principal symbol suddenly gains a geometric meaning. If you get some geometry coming out of the problem, you expect your formulae to become much simpler. So here are the 3 geometric objects that you can extract out of the principal symbol. So the first one is metric. You take the determinant of the principal symbol, you discover that it's a quadratic form in momentum. Not surprising, because you are looking at a 2 by 2 matrix, and the momentum psi comes in linearly. But you can call this thing a metric, the coefficients that appear here. And it agrees with the definition of metric in theoretical physics. So the logic here is that I started with a problem that had no geometry in it, and suddenly I have a metric pop out. It reminds me of the situation when I was young. I started reading Ivry's works, and I complained to my PhD supervisor, I do not understand what is the Beltrami-Laplace operator. Don't know no differential geometry. And he said, oh, don't worry, just think of any operator with variable coefficients. The coefficients will define the metric. So it's a matter of whether you think the metric is the primary object, and then you build some different Laplacian on the basis of this metric, or Dirac operator. Or you think you're just looking at a more or less general operator, and the coefficients of it define what you call the metric. But the metric is definitely here. Second object. Second object is more interesting. It's called the teleparallel connection. So you start thinking, I have 2 points on a manifold, I have a covector here, and I want to construct a covector here which is parallel to this one. How can I do it? Okay, here is the recipe. Solve the system of equations. X and y are different points. Eta, the covector eta is given. Psi has to be found. Gives you a system of 3 linear algebraic equations which can be solved. Give you a definition of parallelism. A specific feature of dimension 3, 2 by 2 case with 0 trace. Once you have a connection, you can introduce connection coefficients. And the concept of teleparallel connection, it's a metric compatible connection with 0 curvature but non-zero torsion. It's the opposite of the Levi-Civita connection. Those who do general relativity know that, okay, the way to do it is to have 0 torsion, non-zero curvature. But this is the total opposite. 0 curvature, non-zero torsion, and everything is written down explicitly. I just don't want to trouble you with formula. Everything is written in terms of the principal symbol. And once you have connection coefficients, you can write down the torsion. Now, the teleparallelism has an interesting history. In the 1920s, Einstein and Cartan hoped to construct a unified field theory on the basis of this idea. There was great excitement to such an extent that Einstein's papers were posted in the shop window of Selfridges and so on and so on. And then Dirac came up with his equation. Everybody forgot about teleparallelism. And Einstein's research career was essentially destroyed. Of course, everybody celebrated his achievements, but specialists to this day do not take his work seriously, the teleparallel work and everything he wrote later. So I think this is the first occurrence of teleparallelism in the setting of pure maths. You just needed to write the second term of the counting function, the spectral function. It's no longer an invention of crazy old Einstein. And the third geometric object, I call it topological charge. If you calculate this number, the these things indicate derivatives with respect to psi1, psi2, psi3, you'll discover that it can take only two values, +1 and -1. This measures the orientation of the principal symbol relative to the chosen orientation of coordinates. So I call it topological charge. Now, these three geometric objects, they essentially define the principal symbol uniquely. So here is an appropriate lemma. If you know the metric, the teleparallel connection, teleparallel charge, you can recover locally the principal symbol up to a rigid rotation. Okay, rigid rotation means multiplication from left and right by a constant special unitary matrix. Such a transformation is never felt in spectral analysis, so you essentially uniquely recover. Now, once I've disassembled the principal symbol into three geometric components, I expect to write the second asymptotic coefficient in a much simpler way via these geometric objects, and sure enough, there is a formula. So this is the point I'm making is that this is a massive simplification compared to the general case. In the general case of an abstract, m by m system on an n-dimensional manifold, you have some integrals here in momentum, in the dual variable. There are no integrals left. I took care, we integrated all of them. We just express everything via torsion, topological charge, metric, and okay, subprincipal symbol is still here. It comes in a trivial manner. Now, regarding testing, is our formula correct? So here comes the second test, and this is where it all started. That's when the doubts started. So let's consider a special operator called the massless Dirac operator. So this will be not the massless Dirac operator considered here, but in curved space. I will be thinking of a single neutrino living in a compact universe. Maybe a strange problem for a physicist, but for a mathematician, why not? So you have this spectral problem. Writing down this problem is pretty difficult because the explicit formula for the massless Dirac operator in curved space is very messy. Spent a long time learning differential geometry. You have to have Pauli matrices that depend on position, and then you have covariant derivatives, and God knows what. But suppose I am a spectral analyst. I'm looking at a spectral problem. I want to know, is my operator a massless Dirac operator? Is there an easy way of answering this question? Okay, there is a technical difficulty, first of all, that the massless Dirac operator acts on spinors. And the components of a spinor do not change under coordinate transformations. They change if you change the frame, but not coordinates. They behave as scalars. And spectral theorists love half densities because you can write the inner product in an invariant way. This is not a problem. You can turn your spinor into a pair of half densities simply by multiplying by the fourth power of determinant of the metric. So there is, you can identify scalars with half densities when you have a metric. So let's return to the question. Can I tell whether my operator is a massless Dirac operator? And here is, the main result of that paper. An operator is a massless Dirac operator if and only if two conditions are fulfilled. Subprincipal symbol is proportional to the identity, and the second asymptotic coefficient of the spectral function is 0. And this is the second test of what we've done. And this is where it all started. At some point, a few years ago, I told my PhD students, now that we've learned so painfully what the massless Dirac operator in curved space is, let us apply Safarov's results. I am sure you'll get second coefficient 0, because the massless Dirac operator, like the Maxwell operator, any other sensible operator, has so many symmetries in it. It has to be 0. And they couldn't get 0. They kept coming back, it's not 0, it's not 0. And then I thought maybe there is a mistake, in Safarov's formula. So this is a simple way of characterizing the massless Dirac operator in curved space. These conditions, by the way, are invariant under such transformations. You can multiply your operator from the left and right by a special unitary matrix functions. They are invariant. Why is this important? because I was cheating when I said the massless Dirac operator. There are actually many massless Dirac operators which differ by special unitary transformation. You can choose your Pauli matrices in infinitely many ways just by multiplying left and right by special unitary matrices. So it covers all of them, this theorem. Now there is another issue that, okay, still there are different, topologically different massless Dirac operators. Not if you have two massless Dirac operators, there may not exist a smooth special unitary matrix function which turns one into another, and this issue is referred to as different parallelizations. On a torus, you have 8 different spin structures, 8 different parallelizations, topologically different. In plain English, for normal people, it just means periodic, antiperiodic boundary conditions. But for geometers, it's some sort of deep thing. But this theorem does not feel the topological difference between different types of massless Dirac operators. Maybe if somebody goes deeper in spectral analysis, you could feel the difference. But the bottom line is that what I'm saying is that the geometry of spinors, the differential geometry, is encoded simply in the microlocal analysis of PDEs. So if you wish, you can avoid reading books on these difficult books on covariant differentiation of spinors. You can just do microlocal analysis of a system of 2 PDEs, and it all just pops out automatically from the condition that the second asymptotic coefficient of the spectral function is 0. I don't think it's a pedagogically good approach, because first you have to spend several years learning microlocal analysis, and then several decades correcting all the mistakes that were made in this subject area. But as a matter of principle, I think it's important. So it makes me think, what is the fundamental object in nature? Is it geometry, or maybe just a PDE? And geometry is a nice way for us to interpret, certain solutions. Now I can do similar things for the massless Dirac action. Massless Dirac action is just a variational functional for the massless Dirac operator. And it's often easier to deal with a variational functional rather than the operator itself. And here is a separate result, which is not in that preprint, which we will publish in a separate paper. So again, I'm working on a compact 3 manifold, and consider an eigenvalue problem with a weight, W. It's 2 by 2 operator, has the principal symbol has 0 trace, and I assume here that the sub-principal symbol is 0. So this spectral problem is totally determined by the principal symbol of the A operator A and the weight, W. Now, no normal spectral theorist would consider such a problem, because you can just exclude the weight, the positive weight. You multiply left and right by W to the power minus 1/2, you just exclude it. But having spent, a few years in the wilderness of theoretical physics, I learned to value gauge transformations. So I leave the weight and just observe that this the spectrum of this problem is invariant under a certain gauge transformation. You can multiply the operator and the weight by a positive function, and the spectrum doesn't change. So let's leave it like this, and then consider the map. So I'm given a principal symbol, and I'm given a weight. I calculate the second asymptotic coefficient. You see, it now doesn't have an x in it. It's the second asymptotic coefficient of the counting function, a much simpler object than the spectral function. So I'm trying to assign a geometric meaning to this second asymptotic coefficient of the counting function. So I take all sorts of principal symbols, weights, and for each of them I get a functional, a second asymptotic coefficient. I do it under the constraint that the determinant of the principal symbol is preserved, because I know that the determinant of the principal symbol is the metric. I don't want to change the metric. I don't want to study gravitational effects. But just formally mathematically, study this map. It should have a nice geometric interpretation, and sure enough it does. It's just a map from a spinor field to massless Dirac action. And the way this theorem is proven is just by explicit calculations. So here is the basic idea. When you are looking at a 2 by 2 trace free Hermitian matrix, and you know its determinant, you don't know the matrix. There are 3 additional degrees of freedom there. And a nice way of describing these additional degrees of freedom is using the concept of a spinner. And that's essentially why spinners were invented, to describe rotations nicely. And you just do calculations, you get the massless Dirac action. So you start with a problem which had no geometry in it, just a spectral problem. A, V equals lambda V. And the geometry encoded in this problem is so powerful that the second asymptotic coefficient of the counting function just has nowhere to go. It has to be the massless Dirac function. It cannot be anything else. But checking it involves a lot of calculations. Now, why did I want that gauge invariance? Why did I want the weight in the problem? Because you see the massless Dirac action has a certain property, conformal invariance. If you rescale the spinor field and the metric in a correct way, it's invariant. And this invariance, the spectral problem, on the previous slide I said you can rescale the operator and the weight without changing the spectrum. It simply translates into the gauge invariance of the massless Dirac action. So the message I'm trying to deliver, if you do properly an analysis, spectral analysis of systems, you get amazing geometry suddenly popping out. But it's inevitable if you don't want to make mistakes. It's just inevitable. It's not as if I was asking for it. It just came up when we started correcting formulae that weren't correct. Now, why am I doing it? On the one hand, I like doing spectral analysis, but on the other hand, there are certain things that have been bothering me. And as this is a workshop on relativistic spectral theory, so this is what has been bothering me. So everybody has their list of favorite equations. And here is my list of 4 favorite equations of theoretical physics. And astonishingly, all 4 contain the same physical constant called the speed of light. There should be a rational explanation. Of course, there is a rational explanation. It's called theory of relativity. For those who don't know it in detail, here is a 30-second description of theory of relativity. God is a geometer. He decided to measure distances in a funny way. Instead of using the normal Pythagoras theorem, which is here, he added a negative term. So this is time, and there is some constant in front. And having decided to measure distances in this funny way, it's called Minkowski metric, he then built up the world using only geometrical constructions. And as a result, this metric appears in all equations, and we get it, the speed of light everywhere. But that's all there is to general relativity, to the relativity. But there is an alternative explanation, that God is actually an analyst. He wrote a system of nonlinear PDEs, and it has a parameter in it called C. But it's too difficult for us to write down this system and analyze it properly. We see only some solutions, we interpret them in our own way, and we always see the speed of light appearing and assign a geometrical meaning to it. But I'm trying to promote this idea, only it's very difficult. I don't see a shortcut here. I just want to continue studying systems of PDEs, preferably non-linear. I started with linear, but I see hope for non-linear already, because when I did this argument, what is the map from the principal symbol to the second asymptotic coefficient, it's already like a poor man's way of solving a non-linear equation. So I solved the linear equation and then said, what happens if I start changing the coefficient? I get a map from the principal symbol to the second asymptotic coefficient. It gives me hope that maybe I will eventually get some results for nonlinear systems. But irrespective of whether I'll be successful in constructing a unified field theory, probably not, I just want to report that I discovered a wonderful mathematical playground. It's just micro-local analysis of systems of PDEs, even linear PDEs. always thought until recently it was all done, and it's not. It hasn't been done. It was never done properly. It was all done with mistakes. There are amazing effects when you just start honestly doing micro-local analysis of systems of PDs. So thanks for your attention.
Time for any questions?
So if you do WKB constructions for the Dirac equation, then I think the phases are always determined by square root symbols, and then we have for the first order transport equation some kind of Bachmann-Michael-Teleki.
That's what you've been spending the last few years doing it.
Yeah.
See, there are several languages people use. WKB method, micro-local analysis. Micro-local analysis is the same thing. We do transport equations, construct phase function. Only we do it absolutely rigorously. In essence, it's the same, but people who do WKB, they rarely reach the stage of a theorem. It's in essence the same, but there are some failures on the way. But what I'm doing is exactly what you're describing. If you look at the preprint, it's full of transport equations and phase functions.
My question was, in your formula for the subprinciple symbol, is this connected to this Bachmann-Michael-Teleki equation? Do you know this?
I don't have the faintest idea. People have been telling me that maybe similar effects were observed in Maxwell's equation. I read, some old and new papers. I didn't see the curvature in papers on Maxwell's equation. Maybe people who studied the massless Dirac noticed this curvature too. If you can send me some link or name, how to find it in Wikipedia, I will investigate. I know spectral theory. I know definitely that people who do spectral theory missed it. Maybe some applied people who studied specifically Dirac noticed all this. If they did things, really, really good.
Any other questions? Let's thank the speaker again.